Hey everybody, this is Larry, this is me going Q3 of the weekly contest 466, Count Both Subarrays. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about this one. So this one is what I would call a contribution problem. You could maybe even call it a sliding window type thing, but yeah, I'm going to call it contribution. And why do I say call it a contribution problem? I think it's a term that only I use, so my apologies if it doesn't mean anything to you. But basically, the idea here is that for every element of the array, it contributes something to the problem, and we have to try to figure out what that something is, right? And phrase it in a way that we can find something that's something in an easy way. And this is one of the inputs, right? And the idea here is that, okay, let's go one at a time. And to keep it consistent so that we don't double count, the way that for this one anyway, I structure as saying that, okay, let's say we're at this current element. We're saying that this is the right-hand side. So we're trying to find the left endpoints to calculate the number of, well, left endpoints that give us the answer, right? Well, for 2, the answer is going to be 0 just because there's no left element, right? For 5, it is also 0 because you know there is a 2, you have to have at least 3 elements, so that's not going to be Gucci. But then for 3, then what happens? Well, you see this 5, and then yeah, so it's too close, and then that's it. This is actually a terrible example, I guess, right? And then 1, what do you see? Well, 1, you could see the 3, but yeah, but then that's it, right? Because 3 is bigger than 1. And because 3 is bigger than 1, that, you know, everything to the left of it cannot be a left endpoint because 3 is already bigger than 1, which it violates one of the conditions where 1 is the right endpoint. And then you have 4, then now you have 3 and 5, so 4 actually contributes 2 to the answer, right? So that's basically the idea. And if you do this in the way that I just described, it's going to be n squared, right? For every element, you look back, no big deal. Right? Yeah. One of the first things that you try to do, of course, to reduce it to O of n time is to make observations, right? And the observation is that, as we said, if we see a number that is bigger than our current, let me change the colors real quick. If we see a number that is bigger than our current number, then we have to stop, right? Because everything to the left of it doesn't matter, right? Fair enough, right? Because everything to the left of it, this is gonna be in the middle, and that number is already bigger than this number, so doesn't matter, right? And then the other thing is that, and this is a poor example for it, but let's say you have a 2 in the middle, right? Well, the 2 we will never need to consider it because we have a 3 here, and because we have a 3 here, this cannot be the other endpoint because, well, 3 is bigger than 2, so then we can eliminate it. And then as a result, if you kind of extrapolate and think of it this way, then that means that because every number, so you have this number, but every number after that has to be smaller than this number, otherwise this number would not be an endpoint. Has to be smaller than this number, then it becomes a monotonically decreasing sequence, right? Because, for example, you have 5, 3, and then everything that's smaller in between, you just eliminate anyway, right? Well, this is because of the 4. And then when you have and that gives me this idea of using a mono stack. Yeah, and invariant behind the mono stack, and as we built it, is that let's say we do keep the 2 for whatever. When we get to the 3, we just eliminate the 2, both on the stack, because we know that on the right side we will never need the 2 again. So this 5 also eliminates the 2 because everything on the right side of the 5 would never need to look at the 2, right? And the reason, and this allows you to save time because you will, when you remove the 2, every element can only be removed once, and as a result, they don't need to check it again. Okay, so then now what, right? One is that, in a very monostack kind of way, when we see a new number, we just kind of, and this gets, when we see the new number 4, we look at the left, and then we go, okay, 1, well, 1 is too close anyway, but it can no longer be an answer to the, it can no longer be the left endpoint to anything to the right, so we eliminate it. Of course, there's nothing to the right, but just to kind of go over it. Same thing for 3, we remove it, right? For the future. But before we do the removal, we go, okay, well, how many things could be the left endpoint of 4? The answer is maybe 3, depending on how you define it. And the reason why I say 3 is because this is the length of the monotonic stack. Everything in between any of these endpoints is going to be smaller. Of course, there is an additional constraint of 3 elements, right? We have 3 elements, so we have to kind of remove the 1 from this, but the idea would have mostly stood. And that's pretty much it. There is yeah, huh. I'm just thinking through how I solved it, and maybe that is not necessary, but in any case, yeah, there are a couple. The way that I solved this is a little bit awkward now that I think about it. That's why I took a pause. My apologies. I am recording this at 2:46 a.m. right after I solved it, so it's it's not perfect. But the way that I solved it is that given a 4, I just binary search for the biggest number to the left, or not the biggest. Sorry, the biggest number that's less than a 4, or the smallest number that is bigger than a 4, and then and then we move, and then that's basically the count. But that's actually not, strictly speaking, necessary. You can actually just remove stuff, right? Because you have the 4, you can actually just pop things off. Because all the numbers in between that you consume, they are valid middle points, but then you get to 5 and you're Gucci. Yeah. And we can just consume them, and then we just kind of count the stuff, and then I think we should be good. Yeah. Okay. I'm gonna show you 2 solutions now that I think of it that way, right? One is what we said, and then the other one I'm gonna optimize it live. So we'll see how that goes. But yeah. But basically, this is it. This is the one that I submitted. This is the one that I did in 10 minutes. Actually, didn't need this binary search, but as I said, I just want to separate the processing and that. Basically, for every index, we have this mono stack. But also mono stack is just a fancy name, but just to keep an invariant that it is in decreasing order. And the reason is because you keep on removing elements that violate it, right? So that's how you get this invariant. But first, we do a count, right? We do a binary search to find the biggest number. I keep saying it wrong. Binary search to find the next greater element than x on the stack, or maybe the smallest element that is bigger than x on the stack, and that's basically it. If it's Leetcode 2, it's fine because you don't remove it, but yeah, and then so the number of things on the stack minus the numbers that are left is going to give you the number of things that are bigger. This is just binary search. I'm not going to go over it in this video, but yeah, it's just binary search. So the length of the stack minus the number of numbers that are bigger gives you the number of numbers that are smaller. So then all of them can be the left endpoint to the current endpoint. The number that are smaller, including the bigger number. And then the reason why we have if count is greater than 0, we minus 1. The reason why we're minus 1 is because we always, the top of the stack is always the last element, because this is before we remove, right? Because we remove things later. So that's why I always have a minus 1. That's it. And then we sum up the count. And then now we process the stack. Again, we have a mono stack, we have a new number coming in. The new number will remove the smaller numbers on the top of the stack, because everything in the future will never use those numbers again. So that's basically the idea. Yeah, and yeah. So with a stack in general, this is amortized. Each element can only be added once and subtracted once, or removed once. So it's gonna be O of n altogether. Oops. O of n altogether. This is O of n. The binary search is O of log n, so this is going to be n log n. And yeah, The thing that I actually noticed while I was explaining it is that I actually don't need to binary search. I can actually combine this into the merge. Yeah. So let's try to do that. So we have this, we pop, right? But every time we pop, we just, that's it. That's the only change. The thing that we just want to make sure, because every time we consume an element, we assume that actually that element could be the left endpoint. The only time you don't add the total may be that if stack of if the index, and we keep track of the index here, if this plus 1 is equal to index, then we don't do it, right? Because that means that we don't have 3 elements, we only have 2 elements because this is the previous index. So we can do that. Is that working? I don't even know. That gives me the wrong output though. So maybe I am wrong. Oh no, you have to do a plus 1. Yeah, okay. Basically, if length of stack is greater than 0 and stack of -1 plus 1 is not equal to index, then we, because basically if there's one element on the stack that is bigger, then yeah, you don't count it, and that's why. Okay, so that looks okay. I don't know why it is so weird. Okay, it's here. So yeah, so that looks okay. Let's give it YOLO submit. Hopefully this is right. Yep. Can't even tell if it's faster than my last one because it doesn't show up on my submissions on virtual contests for some reason. We'll look at it here though, if it ever loads. I don't know if it loads. But yeah, but now that we did it this way, this is going to be O of n time, O of n space, right? Because of stacks. And that's it. I'll even annotate this a little bit. When we remove an element, this element can be the left endpoint, right? Except for if it is the index right before this, because that is the problem constraint, right? Like, I mean, there's no good reason other than there's the problem constraint. So we just don't count it. And that element will always be on the top anyway, whether you consume it or not. And this is the consuming case, right? So yeah, the top of the stack, the invariant is that the top of the stack now is either length 0 or it is a number bigger than x. So if it is not the previous index, then we can use it as the left endpoint, and that's it. I mean, there are a couple of awkward cases because of this 3 length thing, but that's basically the idea. And yeah, this took 231 versus 624 with the binary search, so definitely faster. But yeah, that's it. That's all I have for this one. Let me know what you think. Thanks for watching, and you can watch me solve it live during the contest with the binary search live next. Okay, honestly, nowadays I'm so much less confident because I'm just not as practiced. Okay, pretty okay. Let's do Q3. Numbers of distinct elements are above if 3 elements are minus L plus 1 is greater than equal to 3. The minimum of the 2 ends is strictly greater than the maximum of all numbers. Okay, so like, okay. So this is probably like a mono stack thing, right? Maybe. Let's see. So 2. So at least 3 elements. How do I think about this? So 4. What am I doing? So then I would want to go back. Doesn't have to be increasing, but here all the numbers are in between the 2, right? 3, all the numbers are 2. 2, that's not true. So then monotonically increasing from the back. Yeah, so like I said, it was going to be monostack. I thought it was monostack, but I just want to go confirm it, right? is is it equal? If it's equal, we strictly greater than. So then you want to remove if it's equal. So yeah. But also maybe something like that. Right. 230. That's not right. So 2, no, 5 and 2. Oh, it has to be at least 3 elements. I missed that part. Oh, I didn't miss that part, but my implementation does not consider it. And also, is it accurate? I think this is actually beforehand, but I have to subtract out. What do I have to subtract out? The 3 element case. Right? Yeah, okay, fine. And the top of the stack, the second element, say, is equal to it's gonna be the index. So then if index minus, if this is equal to this plus 1, then we can subtract by 1. Okay. Why is this 1? Oh, because here it thinks. So I'm not quite right. Though I think we still want a monotonic stack, but that's not quite right. I think the idea is mostly right, but some part of it is clearly not. Let's see. Look at here. It thinks that everything in between. You have to do a binary search on. Okay, because basically the biggest number, or the number that's bigger, once it gets to the bigger number, then everything after that cannot be thing, because everything in between will not be smaller than the min. Okay, so that's a little bit annoying, but that's fine. How do I write it? Because you can't just do bisect left because of this part. Maybe we do it backwards. Can backwards work? No, this is symmetric. It shouldn't matter. It's just that this is monotonically decreasing, which binary search is a little bit annoying on. Alright, so we get rid of this for a second. Here we do, okay, so count, you go to, so we want this to be, if it's equal, is it fine? If it's equal, it's fine. And we can take care of this thing in a sec, actually. It's so annoying. Okay, I just say we swap left to the right, so that now we bisect left backwards. No, that doesn't make sense. This is not a hard problem, but it is annoying to write. Okay, fine. If this number is bigger than x, and we want to move right, No, then it could be valid. Could be valid. Actually, yeah. Else, then if it is smaller, greater than or equal to. Well, in that case, it could also be valid if it's equal to. So then I is equal to minus 1. Right. And then now then count is going to be equal to so then left is the index, so then it is going to be length of stack minus left or something. Could be plus. It's very annoying. I think this is fine though. Other than that, but now we don't want this. We want x is equal to num sub. So then we could do one turn behind, I think. If it is exactly the same, do you want to? Yeah, because you can still remove. So okay, so this is fine. But I think this part has to be that. Well, no. I guess this is technically inclusive, but all right. I think I'm right, but it's just getting it correct is a little bit messy. All right. Print x stack left. Total as well. Okay, 2 has nothing, 5 has nothing on the stack. You put the 2. Oh, I wanted to do something like this, but I guess it doesn't make sense because then now it thinks that this is 1. Because I was trying to do this with a delay thing, but you need to pop these off, and this doesn't get popped off if it's delayed. So okay, fine, right? Okay, so then maybe we do something like Alright, well let's just run it real quick just to make sure. Okay, that's just really off. 5 match 2. Oh yeah, that's why it's off. No, because you always, do I always subtract 1? I don't know. This look feels hacky though. Also, this has to be before you add. Even if this is right, it feels hacky. The reason is because the last element you add is always going to be the top element. So that's probably the reason. But honestly, I'm not confident, but I want to YOLO it a little bit. Okay. Because that logic, honestly, is a little bit shaky, that logic, but worked well enough. 10 minutes. Hey everybody, thanks for watching. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. Yeah, and everything in between. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.